This is Hatem Faid. In this video, I'm going to introduce a proof of Riemann hypothesis that is based on Euler-Maclaurin formula, Perron's formula, contour shifting, residue contribution. In this version, rigorous estimates of the remainder terms of both Euler-Maclaurin and Perron's formula are introduced. The video is a brief of the paper that is available at the archive at this link. Riemann hypothesis states that the non-trivial zeros of the zeta function have real part of s equals to half. So assume that s equals sigma plus it, where sigma is between 0 and 1, t is a real number, n is a natural number, and u is a positive real number. Then from the general Euler-Maclaurin formula, we have this equation where bk bar is the periodic Bernoulli polynomial, and b1 and b2 are given by these polynomials. So as n tends to infinity, the left hand side tends to be zeta of s, and the remainder term here can be bounded by this guy, and can evaluate the integral to have this upper limit for the remainder term. Substituting in the above equation, we get this guy. Multiplying by u to the power s, we'll get this equation. From Perron's formula, we have this expression where the star above the summation here means that the last term must be multiplied by half when u is an integer, and the remainder term is bounded by this guy. Using c equals 2 and multiplying by u to the power s, we'll get this equation. To uniformly bound the remainder term, we restrict u to be in a region that is away from the integers from below by a certain threshold gamma. So for example, if we have 3 successive integers, we restrict u to be in these regions to avoid reaching the integers from below. In this way, the log factor in the remainder term would have a lower bound that is asymptotically equal gamma over u as u tends to infinity. Using analytic continuation and contour shifting, we can close this contour to move the vertical line from z equal 2 to z equal 1 minus sigma minus delta, where delta is a positive number that is less than 1 minus sigma. This way, the contour would have a single pole which occurs at z equal 1 minus s. So by the residue theorem, we'll get this equation where this guy is the order of the remainder term according to the domain given above, and this guy is the order of the horizontal integrals using the convexity bound of the zeta function. So by setting t equals u to the power 6, we'll get this equation. Note that sigma star can be written this way. So we'll have another expression for summation u over n to the power s, equating this summation by the one derived from Euler-Maclaurin formula. We'll get this equation. Writing the integral in one sign and denote it as au of s, we'll get this expression. Replacing s by 1 minus conjugate s, we'll get this equation. Let us define iu of s as the difference between these guys, and taking the limit as u tends to infinity, we'll get this equation. Let us study this limit in two cases. The first case where sigma equals half. In this case, both sides are identically 0, which means that for any s along the critical line, this equation is satisfied, whether zeta of s equals 0 or not. For the second case, where sigma does not equal half, suppose that zeta of s equals 0, and accordingly zeta of 1 minus conjugate s equals 0. So these guys vanish. and as u tends to infinity, these guys also tends to 0, which means that the right hand side converges to 0 uniformly. So the left hand side must also tends to 0 uniformly, where g of y is this guy, which can be written this way. To find an asymptotic value for the integral, let us define a smooth cutoff function phi, where phi equals 1 on the near field, where modulus y less than or equal a over log u, and approaches 0 when modulus y becomes greater than a over log u plus a over square root of log u, where a is a positive real number. So we can split the integral into the near field and the far field. For the near field, ju of s, let us substitute by v equal y log u, so we'll get this equation. Using Taylor series, we can expand the g this way. By evaluating the integral, we'll get this expression for ju of s. For the far field hu of s, let us denote gu of y as this function. By integrating by parts twice, we'll get this equation. Simplifying, we'll get this upper bound for the modulus of hu. Actually, this integral can be bounded by these guys. For large modulus y, we have the fractional part of the g function is of order 1 over y squared. And from the convexity property of the zeta function for modulus y much greater than modulus t, we have these orders for zeta and its derivatives, and accordingly these orders for g and its derivatives. And since the line of integration avoids the pole of the zeta function at 1, then g prime, and g double prime are absolutely integrable. So the first integral on the right hand side can be bounded by this integral, which should be of order 1, since g double prime is absolutely integrable. Since the maximum of the modulus of phi prime is of order 1 over w, and the maximum of the modulus of phi double prime is of order 1 over w square, then we have these orders for the second and third integrals, and accordingly hu of s would be of order 1 over log u to the power 3 over 2. By adding the near and far fields, we'll get this asymptotic value for iu of s. Suppose that we have this line segment between it and 1 plus it, and the zeros of the zeta function at sigma plus it and 1 minus sigma plus it. Since the zeros of the zeta function are isolated, so we can have a small disk centered at sigma plus it of radius nu1, where zeta does not equal 0 inside this disk except at sigma plus it. And similarly, another disk centered at 1 minus sigma plus it of radius nu2. Let us select delta such that delta less than the minimum of sigma and 1 minus sigma, and the distance between delta and the minimum of sigma and 1 minus sigma less than the minimum of nu1 and nu2. This guarantees that delta plus it lies inside the left disk and 1 minus delta plus it lies inside the right disk. So accordingly, zeta of 1 minus delta plus it does not equal 0, and accordingly g of 0 does not equal 0. And by selecting a such that sin a does not equal 0, therefore the limit of iu as u tends to infinity diverge, which leads to a contradiction with the previous conclusion that iu must tends to 0 as u tends to infinity. So the initial assumption that zeta of s and zeta of 1 minus conjugate s equals 0 for sigma does not equal half cannot hold. Therefore, all the non-trivial zeros of the zeta function must lie on the critical line where real of s equals half. For more details, please check the paper at the archive at this link, and thank you very much for watching.